All right. Raghu, do you want to share the slides? Okay. Yeah, all right then. Let's start. So, hello everyone. Welcome back to the PC seminar. Today we have with us Raghavendra Rao from IIT Madras, and he'll be talking about parameterized counting in Logspace. So, thank you so much for joining us, Raghavendra, and over to you now.
Thank you, Pratibha, for the introduction. Yeah, good day, everyone. I think whichever part of the world you are in. For people in India, it's good evening, and in Europe, good afternoon. So this talk is going to be on parameterized counting in Logspace. Especially, we'll be focusing on complexity aspects. This is a joint work with Anselm Hack and Arne Meyer from Hanover and Om Prakash, who's a student at IIT Madras. So the landscape of the topic today. So it's in the intersection of three major sub-areas of complexity theory: space complexity, parameterized complexity, and counting complexity. So the intersection between counting complexity and space complexity was studied kind of 30 years ago by Alvarez and Jenner, and in fact, there has been a significant work after that. The intersection of counting and parameterized complexity was done by McCartin and independently by Flum and Grohe around 20 years ago. And the intersection between parameterized and space complexity was studied by Stockhausen and Tonto, from whose work we will be building on today. So today's, yeah, is that fine? Hello?
Yeah, you can go ahead.
Yeah. So today's work will be the intersection of all these three areas. Okay. So we will be essentially building on the work of Stockhausen and Tanto and translate the work there into the counting work. So I'll briefly describe the motivation for our work. So most of us would have seen counting classes which are above P, particularly sharp P and their parameterized variants, sharp W1 and sharp WP, which of course have very, very rich structure, and also the famous Toda's theorem kind of captures the power of counting, in fact, capturing the whole polynomial time hierarchy. So on a similar line, study of counting classes corresponding to space-bounded computation, also they give really rich structures. So particularly complexity of determinant or solving feasible system of linear equations, they are characterized by classes which are built on counting classes. But unfortunately, like in any subdiscipline of complexity theory, we hardly have any unconditional separation. Okay, so that's exactly a fertile ground for parameterization. So parameterization possibly gives a finer classification of these complex classes, also possibly separation between the parameterized versions. Okay. And of course, parameterized study of log-space classes by Tonto and Stockhausen and maybe Banach over a sequence of 2-3 papers. They have introduced parameterized variants of space-bounded computation or space-bounded complexity classes. Okay. So in fact, there are like rich set of natural problems which are complete for parameterized space-bounded complexity classes. So we would like to study the impact of these for counting problems. How do they? So how the counting problems behave when we parameterize in the log space domain. Okay. So in this talk, I'll be basically for the benefit of audience, I'll give a brief introduction to the complexity background, and particularly space computation and space-bounded counting, and then we'll give our results, which essentially is a characterization, definition and characterizations of complexity classes. Okay, so I'll just briefly begin with the space-bounded computation model. So unlike in time-bounded computation, so space-bounded computation model, so we will have the input in a read-only tape. So we assume that, so for example, if the input is in a graph, we cannot modify the graph right away. Okay, so we can only read in an arbitrary fashion. So in the Turing machine model, we will be reading in a sequential manner. And the random access machine, we will be reading any bit of our interest. Okay. The work type is restricted to the space bound. Typically, our interest will be in logarithmic space, so log in the size of the input. Okay. And in case if there is non-determinism, we'll assume that the input is the non-deterministic choices are based on a choice state, okay, which is again read only. Okay. So which basically means a log n space bounded machine can run for polynomial time and can make so many non-deterministic choices, but it can't afford to store them. Okay. So similarly, it can store a portion of the input, whatever fits in log n bits, but it cannot really store the whole input in the work type. Okay, so this is the model that we are going to stick to for the rest of the talk. Okay. So yeah, we'll briefly look at important complexity classes in the classical world, which is relevant to space bounded computation. So L here represents set of all languages accepted by deterministic logarithmic space bounded Turing machines. There are several complete problems for the class. For example, directed forest reachability, that is given a directed forest and two vertices SNT. Is there a directed path from S to T? Another celebrated problem is undirected graph connectivity. Given an undirected graph and two vertices SNT, is there a path, undirected path from S to T? So these problems are known to be complete for the class L. The NL is a non-deterministic counterpart of it. This is a set of all classes or languages accepted by non-deterministic logarithmic space bounded Turing machine. The celebrated complete problems are directed graph reachability and satisfiability of 2CNF formulas. Okay. So in fact, there are also other structural problems, unlike time-bounded computation, that are known to be true in the space-bounded counterparts. So for example, NL is known to be closed under complementation, which in the case of NP, that is a time-bounded counterpart of NL, we don't really know if NP is equal to co-NP, or that is NP is closed under complementation. Okay. Yeah, this is a kind of celebrated result, maybe some 35 years ago. So in a way, I mean, what this makes is hierarchies built over NL, just like the polynomial time hierarchy and so on, they collapse. Okay. But however, the main challenges of separating complexity classes remain. Yeah, the main challenge remains separation of NL and L. Okay. So basically, I mean, you want to check if, or we want to see if testing reachability in a directed graph can be done in deterministic log space or not. This is the primary question in space bounded computation. Okay. So, so we'll just quickly look at the parameterization of the space bounded computation. A natural parameterization is so we allow an additional parameter at the input and allow the computation to use space which is bounded by a parameter. Okay, so we'll allow order of f of k plus log n space. So one might wonder, okay, why not f of k times log n? So that is a technicality, because if we have an S space bounded machine, we can argue that the time for the machine without getting into an infinite loop is bounded by 2 power s, or 2 power order of s. Okay, so 2 power f of k plus log n will be within fpt, whereas if we take f of k times log n as a space bound, it becomes n to the f of k, which is a problematic thing. Okay, so that's the reason why we say whenever we say parameterized log space, the space will be f of k plus log. Okay, yeah. So then the choice state, non-deterministic choice state. Like I said, the non-deterministic choices are governed by the contents of the tape, which is like accessed bit by bit. Okay, so space-bounded counterparts of NL and L and NL are defined accordingly. So para L is a set of all languages accepted by deterministic Turing machines that use f of k plus log n bits of work type space. Para NL, again non-deterministic Turing machines which use f of k plus log n bits of work type space. Okay. So while para L is a natural parameterized version of NL, para NL turns out to be quite powerful. Okay. So just like when we look for parameterizations of NP, para NP turns out to be a very powerful class, and it's not a natural parameterized version that we would like to study. Okay. So particularly of interest will be a parameterization which kind of we should be able to study classes languages within NL with respect to parameterization. Particularly, I mean, parameterization will be of interest only if it allows us a finer, allows us to see a finer structure between L and NL. Just like the W hierarchy gives us a finer structure between P and NP. Okay, so, or FPT and NP. So for this, of use is the notion of bounded non-determinism that was introduced by Chen and Flum, using which they have characterized the W hierarchy itself. Okay, so here we'll restrict the number of non-deterministic steps made by the machine. Okay, so in the case of word RAM model, where so the word length is considered to be log n, so we say that machine is k bounded if it makes at most order of f of k many non-deterministic steps. Okay, or equivalently, if you come to the Turing machine language, we'll say a machine is k bounded or has k bounded non-determinism if it uses at most f of k log n many non-deterministic bits. Okay, or the number of non-deterministic choices is bounded by f of k log n. Okay. So yeah, so in this setting, it also becomes interesting how these non-deterministic bits are accessed, or when these non-deterministic bits are accessed. Okay, so people have also considered the restriction where the non-deterministic bits are accessed only at the end of the computation. Okay, so such computations are called such machines are called tail non-deterministic machines, or we call it as tail non-determinism. Okay, so we allow the machine to run in FPT time, that is f of k n to the order 1 time for some function, computable function of k. But the machine is allowed to use its non-deterministic bits only at the last order of f of k log n steps. Okay, so that is a restriction. So using this, Chen and Flum, in fact, characterized the W hierarchy. I'll only describe WP and W1. So WP is characterized by all problems that are accepted by k-bounded non-deterministic bits, which are FPT time bounded. Okay, so k-bounded basically means limit on the non-deterministic choices, that is f of k log n in the Turing machine model, or in the RAM model, it's f of k. So I just demonstrated quickly with an example. Okay, so example WP complete problem, as we all know, is circuit SAT. Okay, so you can just quickly see how to build such a machine for circuit SAT. Okay, so here the input is a Boolean circuit on n variables. Parameter is k. Want to accept if and only if C has a satisfying assignment of Hamming weight k, that is satisfying assignment where exactly k variables are set to 1. So algorithm is straightforward. We non-deterministically guess a satisfying assignment. So to guess a satisfying assignment, it's enough to guess which of the bits are 1. Okay, so we basically guess k indices, I1, I2, etc., ik. So each of this can be done with the log n many bits. Okay, so we'll require k log n non-deterministic bits, and accept if and only if the circuit on the input evaluates to 1. Okay, so I hope it gives a flavor for k-bounded non-deterministic machines. So all we need to do is guess k indices. So any problem where you want to say, for example, k click or k vertex cover, yeah, any of the problems where the solution space has a subset of size k, you can easily see that they can be done by k-bounded non-deterministic machines. Okay. So in the same article, Chen and Flum also characterized W1 via tail non-determinism. Okay. So in fact, if you consider the same parameters except restrict the non-deterministic choices to tail, then W1 is characterized by such machines, which are FPT time bounded. Okay. So one quick example is parameterized click. Okay. So here, just to recall, parameterized click problem is a problem where we have a graph and parameter k. We want to check if the graph has a k click or not. So all we need to do is guess k vertices. Now the verification procedure. So the verification procedure, all it needs to do is check for k order of k square. In fact, k choose 2 edges. Okay. So for every pair of vertices in this set, v1 to vk, check if there is an edge or not. So only thing here is that if you consider the Turing machine model, you want to access a bit, you will have to traverse the whole tape. Okay. So this tail bound, the bound of f of k log n steps may not work there. Okay. So in the RAM model, I mean, this log n is taken off. We just say f of k steps. Okay. So that is the reason why Flum and Grohe considered a RAM model for the machine characterization of W. Okay. So this k square holds only when the memory access to memory is random. Okay. So that's why RAM model. In fact, we'll be sticking to RAM model, but with the slight change there, I mean, we'll also want bit access. Okay. So yeah, we'll see that later. So yeah, taking cue from the characterization of W hierarchy, Stockhausen and Tonto in fact considered the corresponding non-deterministic computations or k-bounded non-deterministic computation, which are Logspace bounded. Okay, so, and they defined the classes para WL and para W1L. Para WL is characterized by para Logspace bounded k non-deterministic machines. Para W1L is those which are tail non-deterministic. Okay. So again, this log n will be taken off if we consider RAM model. In the case of Turing machine model, we'll need this log n. Okay. Yeah. So in the case of space bounded computation, there is also another finer invariant that is interesting with respect to the access of non-deterministic bits. Okay. So here in these classes, there is no restriction on how the non-deterministic choices are accessed. The machine can go back and forth on the non-deterministic choices. Okay. But unfortunately, even if you consider a non-deterministic log space bounded machine, if it is allowed to traverse the input back and forth, it characterizes the class NP. Okay. So for in fact, in the case of NL, it is necessary that if you see the non-deterministic choices as bits written in a choice tape, we are allowed only read once access. Okay. So to get interesting classes in this parameterized setting as well, we'll need such a restriction. Okay. So we'll look into that restriction. In fact, it was studied by Stockhausen and Tonto themselves. Okay. So here we assume that the choice tape is not just read only, but it's read once only as well. Okay. So we are allowed to traverse a tape left to right. That is, if you have read the first bit and if you have moved on to read the second bit, you are not allowed to see bit 1 again. Of course, you can store it in the workspace tape if there is enough space, but remember that it's only parameterized log space bounded. Okay. So in fact, NL is characterized by log space bounded non-deterministic TMs that access the non-deterministic bits in a read once fashion. Like I said, if you allow multi-way read of non-deterministic bits with the unbounded multi-way read, it in fact characterizes NP. Okay. So I mean, you can just imagine satisfiability can be verified in logarithmic space. Okay. So that's exactly the log space machine, which accesses the non-deterministic bits multiple ways or multi-passes. So yeah, so now we'll consider classes resulting out of this restriction. Okay. Yeah. So this is a notation followed from Stockhausen and Tonto. I feel beta is for, I think, one pass or read once. Para beta L represents set of all parameterized problems that are accepted by Logspace, para-Logspace bounded k non-deterministic machines, but the non-deterministic bits are accessed, sorry for the typo, accessed in a read-once fashion. Okay. Similarly, there is a tail version. We can introduce tail version, which was not really done by Stockhausen and Tanto. We call this as, for lack of notation, we call this as para beta tail L. Okay. Okay, so this is how this is basically copied from Stockhausen and Tanto. This is how the landscape of Logspace bounded. In fact, they also study parallel complexity classes in the parameterized, from the parameterized perspective. Looks like. So there are lots of natural problems which are complete for these classes, para WL, para beta L, and so there are also generalizations that they consider, para beta for all, para d beta, and so on. Will not really focus on them. So all these are characterized by natural complete problems. But of course, separations are no conditional, unconditional separations are known. Okay, so that is the status of parameterized space bounded computation. Yeah, so if there are any questions, please feel free to ask in between. Yeah, so now we'll quickly go over counting complexity. So counting problems are typically, they involve counting solutions. Okay, so for example, counting satisfying assignments, or counting number of clicks, or counting number of paths in a graph, and so on. Okay, so primary interactable class capturing interactability in counting is Sharp-P, which is characterized by counting accepting paths in a non-deterministic Turing machine, or equivalently, that is also characterized by counting satisfying assignments to a Boolean formula. So in his introduction of the complexity class, Valiant, in fact, also showed a surprising result. In fact, he showed that there are problems, counting problems, where the decision version is in P, but the counting problems are NP hard, sorry, Sharp-P hard. Okay. So for example, I mean, he showed that counting perfect matchings, or counting number of matchings in a graph, or computing permanent of an integer matrix, in fact, 0, 1 matrix, they are also complete for Sharp-P. So that is kind of one of the starting points of counting complexity. So in general, whenever we study counting complexity, I mean, what is interesting is if the corresponding decision version is tractable, and we want to see if the counting is intractable or not. Okay, so that is what makes counting interesting or powerful as well. Okay, so in the I think early 90s, counting classes correspond to Logspace have been studied and introduced and studied. I think fairly well studied. Okay, so Sharp-L represents a counting counterpart of NL. It's basically characterized by number of accepting paths in a non-deterministic Logspace bounded machine. One well-known problem, complete problem there is what we call a sharp reach, that is counting number of S2T paths in a directed graph. Okay, in fact, directed acyclic graph. Now, so the interesting aspect here is classes built over Sharp-L. I'll not really go exactly. I mean, hierarchies of classes built over Sharp-L. They, in fact, characterize complexity of several natural problems. For example, determinant, or checking feasibility of a system of linear equations, etc. Okay, so that's the main reason why these classes are interesting as well, because for settling the complexity of determinant, it's worthwhile looking at the hierarchy of classes which are built over Sharp-L, for example. It's called the Sharp-L hierarchy. Okay. So of course, I mean, counting classes didn't really help in resolving L is equal to L question, NL question. Okay, but of course, they also give rise to several interesting questions. Okay, I'll just highlight one interesting question, which is like wide open there. Well, complexity theoretically, it can be stated as whether the class C equal to L is closed under complementation or not. But in layman terms, it's basically the question of testing singularity of a matrix. Okay, so consider the problem of testing if a given n cross n integer matrix is singular or not, that is determinant is 0 or not. Okay. So it is known that C equal to L can be characterized by this problem. That is, testing singularity is complete for the class C equal to L, whatever it means. Okay, you can just imagine it is defined by this problem. C equal to L is defined by this problem. Now, this question is saying, is testing singularity of a matrix reducible to testing non-singularity? So here, by reducibility, I mean Logspace reduction, or vice versa. So this is a wide open question. We don't really know if there is a Logspace procedure which translates or converts a matrix such a way that the resulting matrix is non-singular if and only if the original matrix was singular, or vice versa. So this is kind of one of the prominent open questions in this area. We don't even have a remote approach for attacking this question. So our primary motive for studying the intersection of counting, parameterized, and space-bounded computation is essentially with the hope that we'll get a finer classification or maybe a parameterized answer to this question. Okay, so though we don't get an answer, but we believe the foundation that we lay will lead to such an answer. Okay, so I'll just quickly summarize main results in parameterized counting. So there are counting versions of WP, W1, and so on, the whole W hierarchy. Okay, so this was studied by Flum and Grohe, as well as I think McCartin independently. So the main result to note here is counting number of perfect matchings or counting number of cycles parameterized by the size of the cycle or size of the matching. They are all complete for the class sharp W1. Okay, so this is a result due to Flum and Grohe regarding cycle, and Radu Kottakapan for matching. Okay. Yeah. So our definition, in fact, are motivated by these three complexity setups, I mean, or complexity subdisciplines. So we'll be essentially looking at counting variants of the classes defined by Stockhausen and Tantau. And we'll be attempting to characterize or we'll be giving characterizations of those classes with the natural complete problems. Okay. Yeah. So this is once again a reminder for our model. So we'll assume that the space is bounded by f of k plus log n. Non-deterministic bits are k bounded, that is f of k log n. So only one thing that we'll assume here is we'll assume that input tape has random access. Okay, so that is in fact a small technicality. So we could have completely considered random access model, the word RAM model. In that case, we'll be considering only f of k space and f of k non-deterministic bits. But since we are also interested in the circuit model of computation or circuit characterizations of space-bounded computation, it is essential that we have bit access rather than word access. Okay, so bit access becomes essential in the circuit model, or say for example the branching program model. So that is why we are considering a hybrid model. So the only change from Turing machine is we'll assume that there is random access. That's the main reason there is, otherwise tail non-determinism does not make sense. Okay, because to access a bit you may have to go through the tape, so that will take order of n time. Okay, so then no question of having a time bound of f of k log n towards the end of the computation. Okay, or accessing non-deterministic bits only in the last f of k log n steps. Okay, so I hope the model is fine or clear to everyone. Now I'll move on to describing the classes. So I'll just summarize the classes, the 4 classes, based on how and when the non-deterministic bits are accessed. Okay, so if we allow multiple reads and anywhere during the computation, the corresponding counting class sharp para WL, it's basically characterized by counting accepting paths in such a computation. And if you restrict the access to bits to read ones, the corresponding class is sharp para beta L. If you restrict the non-deterministic bits to be accessed towards the end, that is tail computation or tail non-determinism, with multiple reads, the corresponding class is sharp para W1L. With the read ones access, para beta tail L. Okay, so here tail is explicit. So this tail is basically, so W1 is characterized by tail non-deterministic computation. So hence we put this subscript as W1 here. Okay, so these four are the primary classes that we are considering. So in fact, Stockhausen and Tonto had considered these two classes and this class as well. So this class they didn't explicitly study. Probably they didn't find any natural problems complete or interesting problems complete for that in the decision version. But I mean, in the counting version, we'll see that of course this class also has some interesting properties or interesting questions to be addressed. Okay. Yeah. So I will not go into the formal definitions. I hope with the background setup, the definitions of the class is clear, and the nomenclature is also clear. So W for no restrictions at all. W1 with the tail, beta read ones, beta tail read ones as well as tail. Hello.
Yeah, I think that was by mistake. I guess you can.
Okay, sure. Yeah. Okay. So now I'll proceed to describing some of the important complete problems that we have in the article. Yeah. Okay, so this is again, yeah. So with respect to tail. Okay, so this is how the computation will look like. And again, what we need to keep in mind is f of k log n holds only when we consider Turing machine model. If you consider RAM model, then it has to be f of k. Okay. So I'm repeating this because most of the literature you will see only f of k steps as mentioned. Okay, so where they're referring to RAM model. Okay. So our first problem is a parameterized version of counting S to T paths. So remember that counting S to T paths in a directed graph is complete for sharp L. So we show that the natural parameterized variants, where the parameter is the length of the walk, is complete for sharp para beta L, but also for sharp para beta tail L. Okay. So yeah, the same problem is complete under the same reduction, which is parsimonious parameterized log space reduction. I didn't really say what it is. So it's basically a reduction from problem A to problem B, where the solutions are preserved. Number of solutions are preserved. Okay. So it's just the most restrictive of reductions for counting problems. So then, yeah, most of you might wonder, okay, aren't these two classes equal? We don't really know, because we don't really know if para beta tail L is closed under reductions. In fact, we don't really know any reduction for under which this class is closed. Okay. So, but as a corollary, what we know is if you take the closure of the class under log space parsimonious reductions, it gives sharp para beta L. Okay. So in fact, this is going to be our theme throughout. So in fact, we'll have restrictions. In fact, the same restriction could be complete for two classes, but the reason for the two classes not being known to be equal is the second class will not be known to be closed under reductions. Okay. Yeah, so this is our first result. Yeah, I'll skip the proof to later. I'll introduce one of the most important problems that we study, which also gives characterizations for these counting classes, which is basically about counting satisfying assignments in a formula. Okay. So yeah, so the problem here is, so we have a formula. So let's assume that F is a class of formulas. Okay, it could be first order formulas or second order formulas. So yeah, sorry, first order formulas, but could be some restriction. Okay, so for any class of formulas, so if you, so input here is P from that class, okay, and a structure. You can just imagine an assignment, structure as an assignment in layman terms. Okay, yeah. So now, yeah, so this assignment, there is some restriction on the relations. Okay, so the relation should have arity at most 8. Okay, so what we want is number of satisfying assignments to the formula. Okay, but only condition here is the size of the formula is bounded by the parameter. Okay, so otherwise we'll take the output as 0. So I'll demonstrate the problem with one example. Okay, so sorry, it's not visible, I think. Okay, so let's take F as sigma 0, set of all quantifier free first order formula. So in this setup, input will look like a formula of this form. Say x1 is equal to x2 and some relation on x1, x2. And so a formula of this form. So where these relations are part of the structure A. All right. So now arity A says, so these are like first order relations, atomic relations. Okay. So with respect to an input and with respect to a given assignment, this relation might be satisfiable or may not be satisfiable. That is, you can just imagine R as an edge relation in a graph. Okay. So in that case, arity is going to be 2. If you have a hypergraph with rank k, that is at most k vertices in an edge, then the corresponding edge relation will have arity k. Okay, so this arity bound is basically bound on the arities of relation. So here there is no limitation on how many relations you are going to use. You can use any number of relations here, but the only thing is the formula size should be bounded by the parameter. Okay, so this is a very standard setup. In fact, many parameterized problems, parameterized decision as well as counting problems are characterized by these, and these problems are also well studied from parameterized algorithms perspective. Okay, so particularly, so for example, Kurzweil's formula, Kurzweil's theorem, in fact, is stated for model checking problem, but over monadic second order logic. Okay, so here, so this general problem has no restriction on F, but we will be interested only in first order. Okay, in fact, first order quantifier. Sorry. Okay, so yeah, so the example I wrote is already here. Okay, so one thing is, so we need to know that the model checking problem or counting satisfying assignments is W1 sharp W1 complete even when the formula class is restricted to be quantifier free first order formula. Okay, so it's quite powerful problem. So but yeah, so this arity restriction is what is going to be interesting, but we'll also need further restrictions. I'll describe the restrictions that we'll need. Okay, some special classes of formula. Okay, so we say a formula phi, so typically first order formula is R local. Okay, so let's write down a formula. So let's say R x1 x2, or maybe sorry I'll write it here. This is ANDed with R x3 x4. So this is ORed with x1 x5. I hope it is visible. Pratibha, what I write is visible, right?
Yes, it's visible.
Okay, so here the distance, so I'm just drawing this formula as a tree. Okay, So now this distance we are talking about is, so if I look at the occurrence of x1 here and look at the occurrence of x1 here, so I call the distance between these two occurrences is 2. That is the length of this path, number of vertices in the path. Okay. So our local formulas are those where if I draw this formula as a tree, remember that any expression can be written as an expression tree, right? With suitable labeling of internal nodes. So now in the tree, so what we are saying is distance between any two occurrences is bounded by R. Okay. So in fact, if x1 is occurring somewhere far off here, okay, so we need that this length is bounded by R. Number of vertices should not be more than R. Okay. So that is a restriction. So R local property. So basically, if you draw the parse tree of the formula, which is basically the expression tree of the formula, then the distance between any two occurrences should be bounded by R. Okay. So we denote by sigma 0 R local as R local sigma 0 formulas. So remember that sigma 0 are quantifier free first order formulas, which is basically propositional formulas with first order predicates, okay, as atomic elements. Yeah. So this is the restriction that we are considering. So we show that if we consider the problem of counting satisfying assignments in a first order formula, which is R local, where the RET is bounded by A, this characterizes the class sharp parabeta. Okay. So in fact, we show that P sharp MC sigma 0 R local with RET A, where A and R are constants. The problem is complete for sharp parabetyl. And just like in the case of counting S to T paths, it's also complete for the class, the tail version of it. Okay, which we will see. I mean, it's not at all surprising. But however, if you remove this locality or arity restriction, the corresponding problem. So in fact, remember that P sharp MC sigma 0 is also complete for sharp para W. I mean, sorry, sharp W1. Now this problem is also complete for the Logspace counterpart of it, that is sharp para W1L. Okay, so under in fact the easiest form of reductions for counting, that is parsimonious parameterized Logspace reductions. Okay, so in fact, yeah, so this is again a similar theme which we don't know if it is true for all problems. So just like in this case here, so here there is a similar phenomenon. In fact, there are several problems. I mean, in fact, even in the decision word as well, the problem is complete for two different classes, but under two different reductions. Okay, so this model checking problem is complete for sharp W1 under FPD reductions, but if you change the reduction to parameterized Logspace, then it becomes complete for the corresponding Logspace class. This seems to be an interesting feature for all, I mean, whole of this parameterized complexity classes. Okay, so like I said, I mean, it hasn't been explored completely, but at least in this situation, I mean, there are a couple of examples which actually demonstrates it. In general, we don't really know if it is true, but yeah. So I'll wait for questions, if any, before moving on to proving this. So Pratibha, how much time do we have?
So you can take about like 10 minutes more, and then we can keep like 5 minutes for questions.
Sure. Yeah. Okay. Yeah. So I'll try to give an outline of proof of these two theorems. In fact, the first one. Okay. So from there we'll see how to do it for the, I mean, generalize for the second as well. Okay. So yeah, before moving to the proof, I mean, one open question is, so here there is an extremity. So if you take one of the restrictions, we don't really know how these problems behave or how they can be characterized. So if you consider only R local, but without restriction on arity, or if you consider only arity, probably with only arity, I think it might still be sharp para W1 complete. We don't, I mean, that's one of interesting directions here. Okay, so I'll just give a proof outline. So, okay. Yeah, so let's show the sharp para beta completeness. Okay, so the upper bound is kind of straightforward. So guess an assignment. Three variables and verify. So only thing is the guess can be made on the fly. I'll just demonstrate with an example here. Okay. So what we do is we scan the formula left to right, okay, or evaluate the formula left to right, or we can just consider evaluation, bottom-up evaluation. Okay. So since because of the R local property, so a variable will be required only to a distance of R. Okay. So hence all we need to do is we need to remember order one. So remember order one variables. So we don't have to, so for any, if you guess an assignment for X, it need to be remembered only up to a distance of R. So within a distance of R, we will be reading a formula, so whose length is going to be at most 2 power R. Okay, I mean, so that is the tree depth that you will travel will be at most R. So you'll have at most 2 power R other variables. Okay, so at any point of time, you need to remember only 2 power R variables, assignments for 2 power R variables. So hence it's in parallel space. Okay, so because this is a constant, so an assignment will require log n bits to be remembered, because size of the structure is going to be n. Okay, so yeah, so in fact that is how we reverse engineered a special case which is complete for this. I mean, so we realized that if you put this distance restriction, then the formula can easily be evaluated in so with read once access to the non-deterministic choices. That's essentially the argument. So for completeness, so we will be using the other result. Okay, so reduction from, okay, so maybe we'll give a direct reduction. Okay, so let M be a para beta L machine, that is order of f of k plus log n space bounded, order of f of k. I'll use the same function, non-deterministic bits, read once access, tail non-deterministic. Okay, so let's consider the non-tail version. I mean, tail version is even easier. Okay. Yeah. So here, all we do is, so consider the configuration graph. Okay. So let's say the configuration graph is VE. So then we write a formula. X0 is S. So S is the initial configuration. T is accepting configuration. So then all we do is we say that there is an edge from x0 to x1. Remember, we can use arbitrary number of free variables, first order variables, x1 to etc. etc. xk minus 1 to xk, and xk is equal to t. Okay. Yeah, so there is a small catch to it. I mean, yeah, now we can see that the graph satisfies the formula if and only if there is an S2T path. Okay, but the only thing is, since we are considering the Turing machine model, the bit model, the length of the path could be f of k log n. Okay, which is a problematic case. And that's the reason why in the literature people have considered only RAM model, word RAM model. Like I said, I mean, here too we could have considered. I mean, there are other complications when we go for circuit models where we need bit access. So that's the reason why we stick to Turing machine model with the random access to the input tape. So only catch here is this length of the path could be k log n, okay, or f of k log n. Yeah, this should have been f of k. Okay. Yeah, so for that, what we do is we consider a normal form. So I hope this is clear. The catch, the problem here is clear. Catch length of the path could be yeah. So to overcome this, we need a normalization for Turing machine, the machine that we consider. So what we do is, so in the configuration graph, so instead of say from configuration say C1 to C2, we go in one step. So what we do is we allot k steps, log n steps, sorry, not k, log n steps. Okay, so even then there will be at most polynomial many paths. Okay, so yeah, with that modification we can actually, so what we do is, so this modified configuration graph, or in fact we modify the Turing machine itself slightly. I will not go into the details of it. So this modified configuration graph will be basically representing paths of length log n in the original configuration graph. So with that sort of compression, we can in fact have such a formula. Okay. So otherwise the problem is the size of the formula will also depend on log n, which we really don't want. Okay. So this is for, so when we have read once access or read once access, but now tail, so yeah, there is no additional work that needs to be done for tail. This reduction in fact works for tail as well, because see, evaluating this formula, all we do is, I mean, we actually access, I mean, so I mean, it really does not matter if you how we sorry, this formula works for both. Okay, it really does not matter if you access it at the tail or from the beginning itself. Okay, in fact the same argument works for tail as well. So it's kind of surprising, but yeah, that is how it is. Okay. So Pratibha, how will, yeah, I think we are already. Okay, so I will stop here. I will stop with, yeah. So we also have completeness in the form of counting homomorphisms. And this is the final landscape. So we have a lot of complete problems for each of these classes, para-beta, para-beta tail, counting, accepting paths in. Similarly, sharp para-beta, para-W as well as para-W1. Okay. So in the complete problems are in terms of counting paths or counting homomorphisms or counting satisfying assignments, which are here. Okay. Yeah. So only gap in this is basically locality but unbounded arity, or bounded arity but no locality, that we don't really know where they sit in. And it will also be interesting to resolve this. I mean, what we have done in fact shows that closure of the tail class is the same as beta. but we don't really know. At least I personally believe that these two classes are different. Okay, so and it's probably reachable with the techniques that we have. So I'll conclude with the following questions. Yeah, so when we study counting classes, I mean, it's interesting to look for closure properties. Okay, so we have shown under some of the arithmetic operations, addition and multiplication, but it will be interesting to see if it is closed under monas, that is monas such that if the value is difference, but if the value is negative, then we want 0 as the output. Again, about locality and arity. So how about only one of the restrictions? And this tail versus non-tail. Under closure, it probably, at least in the read once access, it becomes equal to the non-tail. We don't know in general if this is the case. If you close closure of sharp para W1L or even without the counting, closed under parameterized Logspace reductions, does it become equal to the non-tail version? We don't have any clue about that. And there are like, yeah, lots of other directions inspired from the classical, studying gap classes, probability versions, or studying hierarchies of classes and so on. So yeah, sorry, ignore this. Yeah, so please see the full version of the paper for more details. Thank you.
All right, thank you so much for the talk. I guess we can take a few minutes for questions. If anybody if anybody has questions, you can just unmute and ask, or if you prefer, you can type in the chat. Okay, I suppose no questions then. So, all right. Okay. Thank you once again for the talk. It was great to have you.
Yeah. Thank you, Pratibha, for hosting me. Yeah, it was
great.
Nice. Yeah.
All right. So, thanks to everyone for joining us, and we conclude our session for today here itself. And see you all next week. Thank you. Bye.
Yeah. Thank you.